Welcome back, dear students. We are discussing some of the topics from electromagnetic induction, and here we are discussing some of the most important questions of the short reasons which are connected with electromagnetic induction. Here is one of the question, most important question. Make list of similarities and differences between the motor effect and electromagnetic induction in moving wire, a dynamo effect. So here is the answer. So here we are. Both the motor and dynamo work on the same principle, that is Faraday law of electromagnetic induction. What the Faraday law of electromagnetic induction was, we have discussed in detail in theory. Change of magnetic flux induces EMF in the coil. So whenever you want to induce EMF in any of the coil, you need to change the electromagnetic flux. So both requires the magnetic field which produces either the permanent magnet or electromagnet. Both have identical constructions. Both consist of armature ring, and carbon brushes. These are the similarities between the two. So here it is. This is the motor, and other side is this dynamo. It converts electrical energy into mechanical energy. And dynamo converts mechanical energy into electrical energy. So this is the main difference. So electrical current is applied to the coil that causes it to rotate between the poles of the magnet. Some mechanical means is required to rotate the coil in between the poles of the magnet. So mechanically or otherwise, it is required to rotate the coil in between the poles of the magnet. But here it is, when the current passes through the coil, it rotates between the magnet. So ends of the coil are connected to split ring. So this is the third difference. And the ends of the coils are connected to slip rings. Here these are connected with the slip rings, and here it is connected with the split ring. So what was the first difference? Converts electrical energy into mechanical energy, and dynamo converts mechanical energy into electrical energy. Electrical current is applied to the coil that passes that causes it to rotate in the field between the poles of the magnet. And dynamo is some of the mechanical means is required to rotate the coil in between the poles of the magnet. Third one is the ends of the coil are connected to the split ring, but here these are connected to the slip rings. So this was the first question which we have discussed. Make list of similarities and differences between the motor effect and the electromagnetic induction in moving wire. So here is the next one question. It is, for a simple motor, for a simple motor, why must the back EMF always be similar than the applied potential difference? Why it is required? And when it happens? When the armature of a motor starts to rotate, the magnetic flux linking the coil changes. Thus, an EMF is induced in the coil. Such EMF is called back EMF. When the armature of the coil starts to rotate, the magnetic flux linking the coil changes. Thus, an EMF is induced in the coil. This EMF is basically called back EMF, and it is written with this one. And what it does, it acts in opposite direction to the applied voltage V. It acts in opposite direction to the applied voltage V, and if R is the resistance of the coil and I is the current flowing through it, then the relation between applied voltage V and the back EMF is given by. This is basically applied voltage. It is equal to the back EMF which is produced due to the passage of the current which is produced after the coil is rotated and the armature is rotated in the magnetic field. The flux changes and it induces EMF in the coil, and as a result, it opposes the further changes. This is basically IR. So if you look at the back EMF, this back EMF is basically equal to the difference of the potential applied and the difference of the energy which is consumed in the form of potential. And this one shows, equation one shows that the back EMF is less than the applied voltage by an amount IR in a given circuit. It is because, why it is? It is because that when the angular speed of the armature increases, the back EMF also increases. And due to increase in back EMF, the current decreases. Due to decrease in current, the angular speed decreases, due to which the back EMF also decreases. In this way, the back EMF can never exceed the applied voltage. This is the main reason or the main concept. This is one of the strong reasons why the back EMF can't exceed in the applied voltage. Here is the answer in the same question. So we are starting from this one. When the armature of a motor starts to rotate, the magnetic flux linking the coil changes. Thus, an EMF is induced in the coil. Such EMF is called back EMF. It is written with this, it is I, and coil acts in opposite direction to the applied voltage V. If V is the resistance of the coil and I is the current, so according to Ohm's law, we will calculate this. V is equal to IR. So flowing through it, then the relation between the applied voltage and the back EMF is, this one is applied voltage and this is the back EMF, it is plus IR. This will be equal to the back EMF produced and the current passes through the coil of the resistance R. So if you are asked to calculate the total EMF, back EMF, it is the difference of the applied potential and the amount of energy which is consumed by the charges when they're moving through the coil of resistance R. So here it is again explained in detail. Shows that the back EMF is less than the applied voltage by an amount IR in a given circuit. It is because when the angular speed of the armature increases, the back EMF also increases. Due to increase in back EMF, the current decreases. Due to decrease in current, the angular speed decreases, due to which the back EMF also decreases. In this way, the back EMF can never exceed the applied voltage. So with this, we have understood the answers of the two important questions. One is for a simple motor, why must the back EMF always be smaller than the applied potential difference? So you are applying some potential difference, what will happen? We have discussed in detail. And with this, I thank you very much for your attention.